Oh, seems like it's starting. Fantastic. All right. Great. Then let me go ahead and get started then. Is that okay with everybody?
Yes, sir.
Fantastic. All right. So good morning, good afternoon, good night to everybody joining us from across the world. My name is Raul Briseño, and I'm one of the co-creators of the REYES program, and I'm also the chair of REYES. I want to take a few minutes to introduce myself and give you a little bit of taste of what REYES is trying to achieve, and I'll tell you a little bit about the history and the goals of today's to the program that starts today. I figured I'll give you a little bit about my background because I think this largely explains why I feel so strongly about REYES and what REYES is trying to achieve. When I was the age of most of you that are joining us from across the world, I didn't know what I wanted to be, and even if I knew what I wanted to be, I didn't have the tools and the resources to get me to where I am today. I was born in Caracas, Venezuela, which is this little dot that is right here, but it's more beautifully displayed by this picture, which is a mountain Avila right here. Venezuela is a country in South America. And at that point in my life, I didn't know any scientists, and I much less didn't know what physics was, which is what eventually I ended up studying. It wasn't until I went to college that I met that I actually met scientists. And at that time, as a college student, the path that would take me to eventually becoming a scientist was fuzzy at best. For starters, I never thought that I would be good enough to be able to contribute into the field. And I never thought that I would be able to develop the connections that would get me there. Fortunately, I met many wonderful people along the way that served as mentors, and they allowed me to develop the skills and the connections to eventually have the tools that were necessary and the confidence that was necessary to be able to help others. In 2013, I got my PhD from the University of Washington, and then I moved to Virginia as a scientist and eventually as a staff scientist at Jefferson Lab, which is what you're seeing right here. And actually, that's where I'm physically located today. And eventually, I became a professor at Old Dominion. After some time, I became a physics professor at the University of California at Berkeley, with a joint appointment at Lawrence Berkeley National Lab. With this in mind, REYES is designed to help folks like yourself that are probably in a similar situation that I was when I was a teenager. Namely, our goal is to help shine a light into the path to achieve your desired career goals. We hope that whether you end up being a researcher at an institution like Berkeley, Old Dominion University, Jefferson Lab, or that you end up being a software engineer, a medical doctor, a science advocate, that your experience at REYES helps you along the way. Furthermore, we deeply believe that science, technology, engineering, and math, which is commonly known as STEM in the US, that these fields definitely benefit from the diversity of talent that could come from all corners of the world, which is what you reflect. And so with REYES, we're trying to make not only your path clearer, but also the sciences more diverse in terms of skill sets. With this in mind, REYES began in 2020, right at the beginning of the pandemic. The goals back then were to provide free, engaging educational content for folks that were stuck at home. We did this by providing topical lectures and classes by experts. By imposing no restrictions as who could join, we got thousands of registrants from all over the globe. Given the great interest, we have continued to run the program, and today marks the start of our 4th summer session. In addition to providing free topical lectures and classes, now REYES also is able to provide opportunities to students to work with mentors from across the world. In case you're wondering how we're able to run this program with no cost for the students, there are 2 major reasons. The first one, we have had tremendous institutional support. In particular, Old Dominion University solely ran the program for the first 3 years, providing all the technical necessary support. This last year, the University of California at Berkeley has also joined forces in providing additional support. Examples of this collaborative support that is taking place today is the fact that the website is hosted at Berkeley. Meanwhile, the Zoom webinar that is streaming this call to you is being licensed by Old Dominion University. The second major reason that has allowed us to keep the REYES program free to the public is the fact that the bulk of the work is being done by a multi-institutional group of volunteers. As I previously mentioned, I serve as the co-chair of the program. The other co-chair is my very good friend, Giovanna Gennard, who you can see in this picture. Outside of her role as REYES, she's the vice president of external affairs and marketing leader at the PRA group. In addition, we have team members Orlando Ayala, Stephen Berry, Noru Diawara, Miguel Ramlashan, and Rachel White from Old Dominion University. And also, we would not be able to provide this year's REYES session without the help of Sarah Whitner from Berkeley, as well as Dwayne Smith, Tom Odom, and their team from Old Dominion University. Today we have had over 1,000, in fact, over 1,200 registrants. And this is after we just created the page a little over a month ago. So it's really an impressive number. We have registrants from over 70 countries. 75% of you are 18 years or older, meaning the rest are minors. We have over 75% from the outside of the US. So the vast majority of you are not in the US. And in fact, we have about a quarter from India. So namaste to the folks out there. And 19% are coming from Mexico. So buenas tardes a mi pueblo mexicano. We have about 40% of the registrants being female, 56 are male, and about 1.5% are non-binary. 48% of you are currently in college, 21 are in high school, and 17% are in graduate school. So that means that you guys are a very diverse cohort from all over the world with different sets of experiences, and we're trying to serve all of you simultaneously. So that's a challenging task, but we're happy to meet it. So now into more fun stuff. So we have a set of lectures that we'll be hosting that are made possible because of the volunteer speakers that we've been able to gather. We have over 20 keynote speakers from a range of institutions, not just in the US, but also abroad. These institutions include Berkeley, Old Dominion University, but also University of Pittsburgh, IBM, SLAC, MIT, and many others that I don't really have time to mention. The topics that you will learn about are broad. You will learn about the science of bugs, as well as several topics involving science, artificial intelligence and machine learning in different roles. This is a very hot topic, as you know. In fact, we have one talk that is dedicated to ChatGPT, so you should definitely join all these different talks. You will learn about astrophysics and cosmology starting today, as well as many other topics. And so what we're hoping to give you is a little bit of taste of different career paths that you can imagine yourself pursuing. But ultimately, science is not just about dreaming. Ultimately, we need you. Science is about doing. And so we want to get you to the point where you can start doing. In school, you've been learning all the basic rules as to how discoveries occur and what they teach us. But at the end of the day, science requires that you roll up your sleeves and get to work and be able to pursue questions that don't have any answers yet. And so to be able to do this, we've created the mentoring program where we connect you with mentors that will guide you through new research projects. So to be able to run the mentoring program, we put a call out to the world asking for mentors that would be willing to serve and volunteer their time over the summer to work with mentees. We gathered 38 responses for mentors, proposing a total of 32 projects. This means that some of the projects involve multiple mentors. Over 460 of you signed up to requesting to be matched with mentors. So there's a lot more of you than mentors, but many mentors will take on multiple students. And we're currently in the matching process for this. So by Wednesday, some of you will have been matched with mentors. I don't want to go through all the statistics in terms of who has registered to be matched with mentors, but one statistic that I really love is that about 25% of you are first generation students. And so this is really amazing. And, we hope to serve you just as much as everybody else. The expected outcome of this mentoring program is that you will be giving a presentation on the topic that you worked over the summer, and you will write a 4-page report. And then you have the opportunity to eventually publish that report at ODU's library as a proceeding. So that's something that you can coordinate with your mentor if that's something that both of you want to do. Ultimately, both the students and mentors will be giving participation certificates for your contributions. As I mentioned, REYES also hosts free classes. This year, we will only host one live class, which is Python for STEM. This is a class that teaches the basics of coding geared towards problem solving in science. This is a class that me and Ted Rogers at Old Dominion University, we created about 5 years ago. We've hosted this multiple times. This year, we're actually co-hosting it. So I'm co-hosting it with grad students and postdocs, and the first lecture will be tomorrow. Also, I want to remind you that everything that we're watching, so all the talks and classes are being recorded on YouTube. And so previous classes have been already recorded on YouTube. So 2 classes that you can already access are the fundamentals of engineering and the musical flow of stems. The first one just teaches you general introductions to a broad set of basics in engineering. The second and the last one teaches you about how to use computers to be able to make your own music. So with this in mind, I wanted to introduce our first speaker, who's just going to give some opening remarks. And this is Professor James Analytis. I will say a few words. James is currently the chair of the physics department at Berkeley for just one more week, actually. So this is one of the last things that he will be doing as a chair. He got his doctorate in philosophy from Oxford, the University of Oxford, as a Rhodes Scholar in 2006. He then, following his graduate degrees, he served. Sorry, let me just look at here. I have too many windows open. He then served as a Lloyd's Tercentenary Fellow at the University of Bristol, became a postdoc fellow at the Stanford University, which is just around the corner of Berkeley. And there he became a staff scientist in 2010. In 2013, he joined the UC Berkeley physics department as a Charles Kittel chair. And he's just finishing his tenure, as I just mentioned, as a physics chair, where he has achieved done many different achievements, which I don't really have time to cover. But I want to say a couple words. I met James about a year ago when I first was joining the physics department, and something that really struck me about him, other than his great personality and charm, was his great desire to make science more accessible to all. And he immediately, when we started talking about REYES, he wanted to be as fully supportive as possible. And so I thought I wanted to give him the chance to be able to say a few words to those of you that are joining us today. So with that, James, I'll leave it to you. Let me stop sharing my screen.
Thanks, Raul. I really appreciate that introduction. I'm not sure about personality and charm, but anyway, I'm pretty sure it's the reverse. So when I met Raul, it was immediately obvious he was a force of nature. Let me say that. So we were very lucky that he wanted to join the faculty here at Berkeley, and anything that we could do to support these efforts to globalize Berkeley education was we were very happy to help support in any way we can. So let me just say, I think this is just an incredibly impactful program. And it's really a testament to the team and to Raul and his co-chair that have just done just an incredible job putting all this together. At Berkeley, we really see it as part of our mission to globalize education and to make science as accessible as possible, proliferating not only the scientific discipline, but also just making it as inclusive as we can, so that everyone comes together in this scientific journey. You've caught me right in front of my children's daycare, by the way. If you're wondering why I'm on the road, I just delivered 2 kids. So that's another way that we try and be supportive, is that we realize people have multiple pressures and multiple ways of going on in their life, not just the science, and that's part of who we all are as individuals. So let me just say, welcome everybody to this global community, and really glad to be giving some opening remarks. Thanks again, Raul. Take care.
Thanks, James. Yeah, and as James said, I mean, something that we want to try to do in REYES is try to demystify the sciences and show you that we really all are human beings, and that just like we want to reflect the diversity of the sciences, as well as like reflect the fact that we're all human beings and we have multiple roles and tasks. And so, yeah, James is a proud father, and he has his priorities there, but also I'm so glad that he was able to make some time to join us for this opening session. So let me share my screen one more time and give you a little snippet of what you're going to learn about this week. And then I promise you I'll get quiet after that. So thank you, James, for that. So let me just give you a sense of what we're going to be learning about today. So I'll introduce today's speaker in just a second, which is the first one. And then after that, but before I do that, let me mention, so tomorrow at 12 p.m. Eastern Daylight Saving Time, you will have Felipe Ortega-Gama, who's a graduate student at William & Mary, kicking off the Python for STEM class. And he will be partnering with me and others in teaching this class. So make sure to join then. We will be using the same Zoom link for all these sessions. Next, on Thursday at 10 a.m. Eastern Time, you will be hearing from Professor Eric Swanson from the University of Pittsburgh about particle explosion. And then after he's done, 11:30, you will hear from Professor Fiala Shanahan, who will be telling us about a topic that is titled From Quarks to Nuclei, the Building Blocks of the Universe. So don't miss these 3 sessions. And I should say that Felipe will be talking twice this week, Tuesday and Thursday. So just keep an eye out. If you are confused about the schedule, the Zoom link, as well as the schedules have been emailed to everybody that has been registered to REYES. If you have not registered to REYES, there's already time to do this. There's still time to do this. Just go to the website, which I shared in the beginning of these slides. The last thing I'll mention is that everything's being recorded on YouTube. So make sure to go to the YouTube page, which is simple. Just go to YouTube and then look up REYES-STEM, and then you subscribe there, and you'll be able to see all the streams as well as the recordings. So with that, it's my great pleasure to introduce today's speaker, Satya Gontcho, who is Satya Gontcho A Gontcho, who will be telling us today about a topic that is titled Unraveling the Dark Universe. So let me say a few words about Satya. So she's a French cosmologist that had her PhD from the University of Barcelona in Spain in 2013. After that, she worked at the University College London, as well as the University of Rochester. This is before she became a project scientist at Berkeley Lab. In fact, we are both colleagues, and we haven't had the pleasure to meet in person. But she, when we called out invitations for people to be mentors and speakers, somehow she stumbled around this call, and then she reached out to me, and immediately as I learned about her background and her work, I thought she would be a fantastic choice for our first speaker, and my team couldn't have agreed more. She has several recognitions. Among them is she's a Force 30 under 30, and this is quite a. I mean, this is not something that you hear. You don't meet somebody that's Forbes 30 under 30 every day, so it's quite impressive. And this was in. She got that recognition in 2019. That same year, she was a recipient of the Giuseppe Siaka International Award in acknowledgement for her scientific excellence and her strong commitment to mentor the future generation of scientists, which is one of the major reasons why I thought she would be a fantastic choice for today's talk. And she's going to tell us exactly what she works on. But something that I thought was really interesting is in addition to being a cosmologist, in one of her passions is she's also a performing artist, and so she explores different ways of incorporating storytelling that could be adapted to reach a broad set of audience and bring public attention to the wonders of understanding the universe. And I think she's going to touch on this in her talk. So Satya, it's a real pleasure, and I'm so grateful that you agreed to participate in REYES and give a talk. So the floor is yours. So if you want to try to share your screen.
Thank you very much. I'm very excited to be joining REYES, and I think it's a wonderful initiative that you guys have. I'll share my screen, and then I'll turn off my camera to preserve bandwidth. So I wanted to introduce myself. Hi everyone. Okay.
Sounds good. It looks great. So one last thing is that if people have any questions, we'll have a Q&A at the end. You're always welcome to put the questions in the chat, and then we'll get back to them towards the end. Okay. But all right. The floor is yours, Satya. Thank you so much.
Okay. So good morning, everyone. Again, thank you to Raul and the REYES program for having me. As mentioned, my name is Satya Gontcho A Gontcho, and I'm a cosmologist an observational cosmologist at Berkeley Lab. And I'll come back on observational cosmology means. And I'm also a performance artist. Some of the creative work I do brings together art and I'll use some of this to illustrate my points. And, observational cosmologist really means that I want to understand of our universe, what it is made of, where it's going. And so, for that, I want to address how we're using the data that we collect by looking at the sky, why we're collecting those data, why we keep on building new instruments, and how we can use those data to learn new things about the universe that we live in. And so my first instinct when I tackle something new is to pay careful attention to the words that we use. And I'm going to start with the etymology very quickly. So cosmology comes from the word cosmos in Greek, ancient Greek. And that means, or that refers to, the world that we live in. And it's believed that Pythagoras was the first person to use it to actually refer to the concept of universe. And then on the other end, you have logy that comes from logia. It's a word-forming element that means the study of, the theory of. And with cosmology, really, we're trying to understand the universe that we live in, what it's made of, its history, and what might come in our future. And as mentioned earlier, I'm an observational cosmologist. And so that means that the starting point of any investigation that I would do is to simply look up at the sky. I grew up in urban areas, And so that means that I actually never experienced a fully dark night sky, a sky full of stars until I was well into my 20s. And what you're seeing here, it's a picture that I took when I was visiting Chile a few years back. And it's the first time I was able to see the Milky Way with my own eyes. And so I really want to point out that having dark skies is a privilege. But then once you're lucky enough to look up and see all the structures that you can see by eyes already from Earth, then this changes the game and sparks an interest in understanding what's out there. So it's very easy to imagine now how civilizations past had an easier access to those dark sky, but they also had a different, some would say more primitive understanding of the laws of physics. And especially in the past couple centuries, our civilization has made humongous strides in our understanding of the world that we live in. And so we've diligently looked at the sky, which is our past, and we pieced it together to put forward our understanding of the history of the universe. And the idea being that the better that we understand the evolution of the universe up until now, the better we will be able to predict what is to come. And so I want to, place ourselves in that world. So you can see on the left, right here, there's a structure that we can see, and that's the galactic plane of the Milky Way. And what that means is, our home galaxy is the Milky Way, but we're sitting right on the outskirts of that galaxy. And that means that when we're looking out in the sky into the universe, we're seeing the main trunk of our galaxy, and that's what's called the galactic plane. And the way to think about it is if you stand up all straight and then you look at the room you're in, you will be able to see the room you're in. But now as your gaze goes closer to where your foot are standing, or you'll see part of your own body, right? Your legs, your belly, and it's going to obscure the view that you would have from the floor, potentially that's, right behind you. And for us, it's kind of the same thing. Because we're so on the edge of the Milky Way, actually for a part of the sky is going to be obscured by the body of the Milky Way. And it's the blind spot that we have, if you will. Now, if we change our viewpoint, keep in mind, we haven't mastered, any type of intergalactic travel. So what I'm showing you here, it's not a picture of our galaxy, but it's a picture of a galaxy that looks very much like ours, right? So we live on Earth and we're on the edge of such a galaxy, and we're part of a collection of planets that are orbiting around a star called the Sun. And then, the Sun is just one star amongst many others, like actually hundreds of thousands, millions of stars. And in the same way, our galaxy is just one in the many billions of other galaxies in the universe. It's not even a particularly big galaxy. So everything that we know it from the point of view of sitting right there at the edge of that one unremarkable galaxy, right? We know it from Earth. And this corner of the universe is where we developed our understanding of the laws of physics. And that brings us to one very important postulate that I want everyone to keep in mind, is that we as a scientific community, we assume that the laws of physics are the same everywhere in the universe, and that there is nothing special about our place in the universe. So anything that we understand here that works here, then that will be applicable anywhere else in the universe. Now, this picture actually I took also when I was in Chile a few years back with a very powerful camera that was attached to a telescope. Now, I want to ask you, You know, if you have such a camera, then what would you do with it? With my team, we used it to diligently take pictures neighboring one after the other of the northern hemisphere of the sky that you can see from, you know, the northern hemisphere on Earth. And basically all those pictures put together look like this. And you see this kind of U shape that's blacked out. That's the blind spot I was telling you about. This is where, when we've taken pictures, we would be looking directly at the trunk of the Milky Way. All of those like mosaic of colors are actually real images of the sky that you can see from Earth. And that represents about 1/3 of anything that we can see from the night sky on Earth. Now, you know, if you zoom in and zoom in more and more and more, you get to something like this. And now you start to be able to recognize that the dots are actually galaxies. And, you know, as you can see, this is now a very, 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 very zoomed in part of all the pictures that we've taken. But you still have hundreds, thousands of dots that corresponds to galaxies there. And for each of those dots, we have two coordinates, say longitude and latitude. And so that we basically have it mapped in 2 dimensions, right? We have something flat, and we're able to say on that flat thing where each of the dots are. But it would be so much more informative if we were able to switch it to 3 dimensions. And for that, we use a technique called spectroscopy to identify the distances of each galaxies. And I'll come back to how this technique works. But for now, let's say that all the closest galaxies, now we're identifying them in blue. And then galaxies that are a little bit further, we're identifying them in yellow, and even further away in orange, and even further away in red. What you're seeing now, if you take that information and you put it into perspective, is blue closer than yellow, orange, red. And what you're having here is a perspective. You've put in perspective all of those galaxies. And you probably also heard that nothing can travel faster than light. And it's true, light travels very, very, very fast, but all the same, the speed of light is finite. And what that means is by the time light from distant galaxies has traveled all the way to us, and we read the information carried by that light, the information is already outdated. And so the deeper you look, the younger the universe you're looking at. And so in that perspective I'm showing you, not every image that you've taken shows you the same period of the history of the universe. And so if you do that with many, many, many images pointing at different part of the sky, you're going to have, first of all, a larger 3D reconstruction. So instead of that little patch of the sky where those dots are taken from, now imagine doing this with 1/3 of the entire sky that you can see. And now, instead of, it's closer, it's further away, you're also having an information that is a timeline of the universe. And so essentially, I've shown you that we know how to turn something that's flat, that's 2-dimensional, into a 3-dimensional map of our universe. And, that gives you longitude, latitude, and the distance from us on Earth. But also this distance from us on Earth, those different slices of depth that correspond to different snapshots in the history of the universe, in the cosmic history. And so, let's say this is what we had. Now let's flatten it and switch it to this chronology of what we've reconstructed already happened in the universe. So we know that the universe started to exist with the law of physics, the laws of physics as we understand them, fine. And then it went from a soup of elementary particles, which I believe the speaker on Friday will tell you about. So all of these elements were in a very nice and then the universe itself started expanding very fast, and it's called inflation. And at the end of that phase, it transitioned from being opaque, which means it was so small that particles were bumping into each other all the time. And so the photons couldn't go anywhere. And then because the universe expanded so fast, there was more space in between particles. And at some point, they stopped bumping into each other and it just started traveling without meeting another particle on their way. And that's when light started to propagate. And that's now when the first light, called the cosmic microwave background, was emitted. And when that started, then finally structures, what we call structure is just a conglomerate of particles. So that looks like stars, and then stars get together and they make galaxies, and galaxies get together and they make galaxy clusters. And so all the while those structures are forming, the universe keeps on expanding. And so here on this picture, you can see the younger universe with the period of inflation, the first light, and then all of those structures. And as the universe expands, the universe also, becomes older. And this arrow is our view from Earth on that history of the universe. We see closer, what's closer to us is an older universe. And then as we go into deeper ends, what we're seeing is a younger universe. And so by taking a lot of those pictures and measuring very precisely the positions of galaxies and things that we can see on those pictures, then we can study how galaxies are distributed, in different places of the universe. But most importantly, if you do those slices of depth, you can study how galaxies were distributed at different moments in time. And you would also maybe expect, galaxies to be distributed at random, but actually they're not. They follow a pattern that we refer to it as a primordial pattern, in the sense that it stems from, conditions in the very early universe. And it's in a sense, the same way that bones are, the skeleton that will inform where the muscles and the veins in your body are. Well, this pattern of dark matter informs where the matter that you can see, the regular matter, will be in the universe. And so, dark matter is really responsible for the distribution, but it's following a certain pattern that is the circular thing that you see now. So if I were to take snapshots at different moments in time, so let's say one at the first light, one when the universe was a teenager, and one at the current age of the universe, if I take snapshots, so pictures at these different moments in time, this is what you would see for looking at the same place. So going from left to right, so from a young universe to an older universe, in the first light, there's, this circular pattern that you can observe. And then as time passes, this gets blown up. And as first stars and first galaxy form, they will preferentially form on the area of that pattern. And then as time moves on, you see there's more space. The structures are bigger, but they preferentially fall still where that pattern is. So what really you want to remember is this primordial pattern. You will find it in where galaxies are located, and you will find it at every stage of the history of the universe. But due to the fact that the universe is expanding, we notice that this pattern has different sizes at different moments in time. So just again, taking a step back and recapitulating, we have this primordial pattern, which actually is called the Baryon acoustic oscillation, BAO. And we know that this pattern has a size that depends only on how fast the universe is expanding. And now I am informing you that the force responsible for this accelerated expansion of the universe is called dark energy. Dark energy is the force responsible for pulling the universe apart, essentially. That's what we know about dark energy. Now, we would like to know more about it. And one way to learn more about it is to track the size of this primordial pattern and see what we can learn then about dark energy. And the way conceptually that this works is if this pattern is blown up as the universe grows, now you have theorists that are sitting somewhere, with a chalk and a board and are thinking, well, what theory, what explanation can I come up with of what dark energy is that would explain the pattern, having size 1 at a given moment, and then size 2, and then size 3. And so that's the red gives you the first theory of how they're predicting that the expansion of the universe is going, considering their theory. But then another theory is going to be this prediction. And maybe a third theory is going to be this prediction. So you see, these are slight changes at different moments in time, but they're all, but they all predict slightly different evolution of the size of this pattern at different moments in time. And if you have different snapshots and you can measure the size of the pattern in those snapshots very precisely, then that's when you're able to discriminate, which means to differentiate between the predictions that match reality, right? That match what you measure in your data, and put aside the predictions that do not match what you're showing, what you're measuring in your data. And so this process of, putting theory against data and then eliminating the theories that don't work and, improving on the theories that kind of match, but not totally, that's the beauty of the scientific process. And really, right, if you create those very large map of the universe, like the 3-dimensional map, then you're able to do that process of measuring the size of that pattern at many different moments in time and comparing it to theory all over, with a very big volume. And that allows you to have a mechanism to understand and probe what the nature of dark energy is. And it's very exciting because out of everything that makes up the universe, dark energy makes up about 70% of the universe. Most of the universe is made out of that thing, that force that we don't quite understand. And in the same way, 25% of our universe is made out of dark matter, which is, I was telling you, the skeleton, in a sense, of the universe. That's where that decides where structures are going to form. That's the backbone of our universe. And then the things that we can see, right? The things that shine, the particles that you'll hear about in the upcoming talks, the protons and photons and electrons, and that, the photons that emit, that travels to you, that are emitted from stars and galaxies, that only represents just 5% of everything that's in the universe. So just to give you a little bit of context as to why we're so excited to understand what dark energy is. But now this is our science goal. This is our motivation. Now the question is, what are the technical challenges that we've overcome in order to be able to address these science goals? What are the technical prowess that we have had to accomplish and still need to do in order to get us to understand why the universe is accelerating the way, like its expansion is accelerating the way it is. So back to my favorite, plot so far. So I'm gonna summarize what we've learned. We are, let's say, we're dark universe detectives, and I'm saying dark universe because we have universe is mainly dark energy and dark matter. And I just want to be clear, dark is not that it's not to do with the color of this matter, of this energy, but it's really to do with our understanding or lack thereof of what those things are. When you're referring to European history, you call the Dark Ages, right? The Middle Ages, the area of history where humanity just had no emphasis on the pursuit of knowledge and was in the dark. That's what we mean by dark energy and dark matter, is we know very little to nothing about it. And so we want to learn about them. That's why they're named the way they are. So, okay. You're dark universe detectives and you want to understand what the dark components are. And so you start your investigation by putting together your first and actually your most powerful clue. And it's getting together this three-dimensional map. So you use 2D images, two-dimensional images, something flat, and your know-how of measuring precisely distances in the universe, and you create a 3D map. And then by doing so, you're simultaneously recreating a timeline of the evolution of the universe from right now, when the universe is quite old, all the way to when the universe was very young. And the primordial pattern of dark matter is in that ring, or actually spherical, pattern, is imprinted in the matter that you can see, namely in the way that galaxies are distributed. And you can measure the size of that pattern at different depths in the map, which means that you can measure the size of this pattern at different epochs of the expanding history of the universe. And by looking at how much that pattern has been blown up, has been stretched, and comparing it to theoretical prediction of what dark energy could be, then you can rule out certain theory and keep investigating the others. Now let's see to, what instrument we've had historically to create that map and how we've gone about developing it. So here, snapshots. I really want to highlight how our level of technology influences the quality of the map that we can build. And I'm just going to focus on the past 30 years. And simultaneously, I hope I'll be able to answer for you the question of those astronomers. They're always asking for money to build new telescopes, bigger telescopes. So they always want to build them at the same place and looking at the same patch of the sky. So is it really, questions that my grandparents would ask is it really useful? Are you seeing new things? Why do you want to look, at the same place again? And what does it bring you? Well, let's have a look. And I'm going to start in 1992 with a satellite called the Cosmic Background Explorer, COBE, that was sent to take pictures of the very first light of our universe, the cosmic microwave background. And the technology at the time allowed for, and I'm not going to show you astronomical images here. I'm going to use some of the artistry I work on in my free time, because I think it gets the point across a little bit better. And so let's say that the quality of the images that COBE was able to take is this very pixelized picture. because it's a satellite, it took full view and was able to, get out of the issue of having the main trunk of the Milky Way obscuring part of the image, but still you had, again, quite pixelized. And then during the same decade, we also had ground-based, so telescope that were on Earth that were observing, parts of the sky, but it was quite uncoordinated. So you were looking at, some parts of the sky, some others not. And so that's why you have this still pixelated, but batches of images here and there that when you put them together, you can see it's not very well coordinated. And then let's say that you skip a decade and onto 2003, now you have the Wilkinson Microwave Anisotropy Probe. Everyone calls it WMAP. And it's another satellite that was at the time the state of the art of what we knew at the time. And we got a slightly better image of this first light. So look very closely. This is what we had with COBE, and this is now what we have in 2003 with WMAP. So you see that it's less pixelized. So we've already made an improvement. Cool. But then also starting the year 2000, you now have a coordinated ground-based effort to start to systematically measure the positions of the galaxies over the sky. So now it's more of a coordinated effort. The hourglass figure that you see is how I represent the main trunk of the Milky Way, obscuring part of your image. And then you should still also notice that our technology didn't allow us to go very deep in the sky. So we could only see the brightest and the closest object, which is why we're having a picture of the universe that's already pretty old, right? And another way to think about it is also when you were doing photography in the 19th century, you had to sit still, like very, very still for a minute for the photographer to be able to take your picture, right, in your three-piece suit. Well, because measuring the distances of galaxies is so time consuming because they don't send many photons, you need to have your, to collect many photons for a long amount of time in order to get enough light so that you can actually see something on your picture. So if you're observing one galaxy after another, you do them one by one, it takes a lot of time. So that's why also we don't have as large of an image as you could see on the left with double. So this is what you had in the 1990s, and still in the 2000s, you see this coordinated effort put you with a slightly better picture. Cool. Now, what happened in the 2010s? Well, we had the Planck satellite that also, again, was looking at the first light, and it gave us a incredibly high quality image of the first light. And then now, as far as what's happening on Earth, you had what was called the Sloan Digital Sky Survey that found a way to take pictures of, and measure the distances of individual galaxies a lot faster. So that's why you had before in the 2000s, the image was smaller and more pixelated. And you see that now in the 2010s, we haven't improved the quality of the image. It's as pixelated. However, we have larger images because we're able to look at more things. But also now instead of one, we have two images. And that's because we're able to see where we have more sensitive instruments. We're able to see deeper. And so improvements. Now, my favorite decade so far, the 2020s, that's exactly what we're in the middle of. So you have other CMB, cosmic microwave background surveys that are ongoing and improving the quality from Planck. but they're still in the works. But now we have the project that I work on, actually, that's called the Dark Energy Spectroscopic Instrument. And that is from the ground, looking up. Now you can see that, first of all, you're not quite as pixelated as you were before, but also the images are even larger than they were. And that's because we're able to measure precisely the distances of galaxies much, much, much faster than we were before. And the quality of our instrument the sensitivity has, increased a lot. And so we're not quite as pixelated, but we still have the hourglass shading that we're observing from Earth. So our galaxy is obscuring part of the view, right? So you go from a smaller image to now a bigger image. And why am I showing you this? Let's summarize. In the 1990s, you had two images, super pixelated, and the one from Earth is quite obscured. Cool. Now in the 2000s, you have still two images, but a little less pixelated, a little less shaded. Okay. Now, in the 2010s, we go from 2 to 3 images and a little less pixelated and a little larger field of view. And now in the 2020s, we have 5 images and we have a much better quality of view. So the reason I'm showing you all this is you can see that the game sort of is, sure, we're looking at the same parts of the sky, but we're always improving the quality of our instruments. So we're getting things that are not quite as pixelated. And then what we're trying to do is always to have more and more and more images, meaning more slices of different depth of the sky. I don't know if you can see where I'm going with this, but if you put in chronological order, high quality images, what is it that you're actually trying to do? If I put all of these images together, I am getting a high resolution movie. And then I can see from those images exactly what happened, because now I've literally, a movie is a series of images in a chronological order, and literally the information that we're getting from the sky, some of them are they're all outdated by some amount. So you're literally taking pictures of what happened, putting them in order, and you're able to then see exactly what happened in the past of the universe. And so what that means for a comprehension of the universe is, by consistently improving on the quality of the images that we take, on the number of galaxies that we can measure, we become increasingly capable of recreating a movie of exactly what happened in the universe. And then, it's going to be all the more easy to test our theories and refine our models to say, okay, well, dark energy is this and dark matter is that. And dark matter has allowed, the matter that we see to cluster, to get together in this way and not that way, because literally we're able to see it precisely. So I thought that was pretty neat. Now, because I work on this state-of-the-art project that's called the Dark Energy Spectroscopic Instrument, I want to show you some of our real data and just give you a very quick snapshot of how we work, because we are at this moment in time the only experiment on Earth that has created the largest 3D map of the observable universe ever created by humanity, and we're really at the forefront of what we know to do. So I'm going to again go back to that picture. So first of all, we need to know we've taken pictures of everything that we could see in the sky from Earth, because we wanted the positions of where the galaxies were, and that's called photometry. It's taking pictures of things, and then in those yellow circles, we identify in those pictures all the galaxies that are of interest to us. And then we do what's called spectroscopy that I already mentioned before, is that for one of those yellow circles, then you go to the right-hand side of the image I'm showing you. And what you're looking at is a spectra. And that means instead of just counting, photons and where they are, right? That's the concept of an image, is you just count how many photons are coming from this direction. And that gives you, oh, here is very bright, here is not bright. And then you kind of get an image. Well, for us, we just focused on one object and we say, how many photons are coming from this object, but how many blue photons, how many green photons, how many red photons? We want to know exactly the number of photons of which color that are coming. And that's on the right side, that's the spectrum that you're looking at. And this actually gives us a very, very precise way to know the distance of a galaxy. And so that's what DESI does. But instead of, DESI is here. That's a picture I took last time I was at Kitt Peak National Observatory in Arizona. DESI is located in this big mushroomy telescope. And just so you can see how big it is, that was me when I was working in London, next to just a slice of the optical part of the instrument. And then on the right-hand side, you see a taller human being than me next to the instrument when it was being assembled, and you see it's huge. And all of this big barrel that I was showing you was a series of lenses that bring the light on what you're seeing here, the focal plane. I don't know if you can tell properly, but all what you're seeing is 5,000 little robots, and they have motors and they have rotating heads, and each rotating head has a fiber optic cable attached to it. And basically those 5,000 little robots, they dance around and they're able to, match what they're seeing on sky and bring very precisely the fiber optic cable on one galaxy. And then the fiber optic cable will collect all the photons from that one specific galaxy and bring it to us so we can count how many photons of which color, so we can take the spectra of that galaxy. And that means, and we have 5,000 of those robots, which means that instead of measuring, one by one galaxy and then another, we do 5,000 galaxies at a time. So that's why we're able to have a high volume of measurements of positions of galaxy very quickly, because we can do 5,000 at once. And just to show you that I also sometimes touch instruments, and that it's very much also hardware driven. This is in 2021. I went to the telescope and helped do an instrument upgrade. So this is, part of the back end of this of these little robots that I was working on here. And then what do we collect all of these images, and you may think it's very abstract, but here I'm showing you real data that we've collected for the first year. So DESI is going to collect for 5 years the position of galaxies, and we've already completed a little bit over 2 years now. But what I'm showing you is all the data that we have collected for the first year of DESI. And these are the real positions of galaxies that this is real data that I'm showing you. And we're zooming out, and you can see that, galaxies are grouped together, and you can see sort of an underlying pattern and, structure in the way that all of those dots are. And as you're zooming out and zooming out and zooming out, you'll start seeing the footprint that I was showing you earlier of 1/3 of the sky. You're going to start seeing it appear, and you'll see where we still need to observe more to keep covering. But this is coming from a planetarium movie that we put together that's called, unsurprisingly, 5,000 Eyes, because we're really also in the DESI collaboration want to try and bring our scientific progress and advancement to the general public as much as possible. So you can see now in the middle of the footprint, and it's kind of looks like also like a mouth that's open looking to the right. All of these are data that we still need to take. But now you can see how all those individual galaxies match this 2D image that I was showing you at the beginning. Yes. So, go see, if you want to learn more about this mapping of the universe, you can go to the nearest planetarium to you and request for them to show the 5,000 Eyes movie. It's entirely free for them to download. And it's a really cool 20-minute video. And I hope that I've been able to, show you the mechanism that we use to take advantage of just taking pictures and looking up at the sky. And then from that, reverse engineer what happened in the past of our universe and show you a little bit, get you excited about that process. And I'll be happy to take your questions now.
Well, before we do that, Satya, thank you so much. That was really great. I hadn't seen those videos before, so I was really amazed to see that. You already have a lot of questions. I'm trying to figure out how to organize this. Maybe let's organize it in terms of foundational questions, maybe. Let me start with a more basic one. So the first question that I see that perhaps is simplest is, could dark energy be considered a fundamental force? So I guess just on the more basic, how do we understand dark energy right now, and how could it fall, even though there's still a lot of open questions about it.
Yeah. So by fundamental force, I think, you mean electromagnetism, strong and weak interactions. So that would be something that has, is our understanding of the physics, as in it works everywhere the same. What we've noticed for dark energy is it acts at very, very large scale, but not at smaller scales. And really the only thing that we know about dark energy is it acts at very large scale. It acts as a sort of anti-gravity, as in gravity put things that are massive and pulls them together. And dark energy will have the opposite effect. And that's about what we know. So really, as many theories that reproduce those effects and this way of acting on the universe, as many possibilities. So for now, saying whether it's how to classify it as a fundamental force, you would first need to, I feel, have a stronger identification of what it is. So it's a really exciting open question, and we need younger scientists to join us and help us answer those questions, because as you can tell, it's time consuming, and the progresses have been humongous in the past 30 years, but we're still are well on our way to get the answer.
Great. Yeah, we have a couple more questions about dark energy. I mean, we have a lot more, but maybe two that perhaps are correlated is, did dark energy originate from the Big Bang? And then how is dark energy to be correlated with inflation?
So what we've observed is dark energy, its effect has become stronger and stronger the larger the universe was. So we can see its action now very well because it's accelerating the expansion of the universe. And so the way that that we often phrase it is, dark energy turned on at whatever moment in time. And the working assumption, like one of the main working assumption, was dark energy's always been there, but was a force smaller, or that wasn't expressing itself in a noticeable way until it actually turned on more recently. So that's one of the main working hypotheses now. But again, different models have dark energy be different things at different moment in time. And so to tie it in, how it acted during inflation, how it acted at different moment in time, these are all, active questions. And so there's no definite answer that I can give you there. And I just see one question that says, how many galaxies have you mapped out so far? So this one, I want to place that we've mapped out in the span of 2 years, right? Just 2 years, we've mapped out 20 million galaxies. To give you an order of magnitude, when I was doing my PhD at the beginning of the 2010s, in 5 years, we had mapped out, I want to say of the order of like 1 million. So we're just doing like orders of magnitude better, and we're not done. At the end of the 5 years, we'll have about 40 million galaxies. And so that's why literally we're creating right now the largest 3D map of the observable universe, meaning of anything that we can see that humanity has done so far. And that's with, experiments that are running now. And a few others are due to a few other experiments are due to compete and complete the dark energy spectroscopy instruments. And so the next decade is going to be extremely exciting in terms of new data and hopefully new discoveries.
Only 40 million. That's a crazy number. All right. Okay, so you're reading the questions. Maybe I can shoot another one, or you can pick one that you want. You have more questions than probably you have time to answer. Maybe here's another that is perhaps more physically motivated. So why is it that as we look further away in the universe, the masses of stars seem to be increasing even though we're looking back in time? So
I will say, what is it? I do not know the answer to that question, because I care starting the size of a galaxy. I will say I do not know much about smaller objects than galaxies. I'm sorry.
Okay, I'm trying to dissect this one.
Yeah.
Other than the time-consuming factor, what are areas DESI could improve upon?
So as I was trying to show, with less sensitive instruments, we could only go to a certain depth, because the further away something is, the fainter it is, so the harder it is for us to look at it. So as we improve the sensitivity of our instruments, we're able to go deeper, so further away from us, but also then get information that are, further back in time. And one way is to increase the sensitivity of the instrument. And then the other way is also the longer you're exposing your picture, the more the more photons you're collecting. So you're able to see fainter objects, but then that also means you pick up more noise. And having performant instruments, yes, that for which you can minimize the noise, you can understand it and subtract it properly, and you can simultaneously observe many of those. So that trifecta gives you, if you can improve on all of that, you're able to reach deeper into the night sky that you can observe, and so you're able to reach different epochs of the universe. And the Rubin Observatory, also referred to as LSST previously, it takes only pictures, right? Just photometry. And so there will be able to go much deeper than anything we could have done with photos before. So that's, one way to do it. But then DESI, for example, uses photos, but then collects spectra, because regardless of what happens, spectrometry is always better at measuring distances. So you have, with a picture, you pick up everything that's on your field of view, and so you're able to get maybe more galaxies than we'll have with DESI so far, but you can only measure their distances to you with less precision. And then DESI, for example, will pick a subset of all those galaxies and will measure very precisely how far they are. And so we have different instruments that have different strong points and that look at complementary parts of the sky, not overlapping, but complementary. And then if you're from, on Earth, then obviously you have the Milky Way that obscures part of what you're looking at. But then you also have the atmosphere. You have, different systematics and uncertainties that are added. But from Earth, you can make more cumbersome instruments, and you can tweak them and they're cheaper to make. But then you also, and someone I saw mentioned the Euclid satellite, for example. So satellites are great because they since they orbit, they can get around having the Milky Way in their view. And then because they're in outer space, they don't have to subtract or correct for the atmosphere. But because they're in space, you can only take in space with you what the rocket can carry. And so it needs to be smaller mirrors, less fragile, and basically a little bit more less complex engineering. And so that means that also your field of view is smaller. Like from Earth, you can make very large mirror. And so you can look at things like a high volume of things. With satellite, you're going to look at smaller things that you need to put together. However, you get much more precise measurement of certain things. And so the game actually, and really a point of importance for the next decade, is going to be, how do we put together all of those pieces of puzzles that are, again, just slightly overlapping in different ways, but also, but not perfectly designed to fit all together. And how can you learn from one piece of the puzzle over there that overlaps with this? And then how can you, from what you learn here, move it to two other pieces of puzzles and just basically take broken down pieces of information and try and make it fit all together. And that ties back to now one other field that I see you're going to hear about in the REYES program. People in astronomy are turning to machine learning. And so it's really, machine learning is a fancy word for statistics, and it's a tool, and it's a very powerful tool, and it's really cool. But I want to, emphasize that it's just a statistical tool that is designed for high volume data. And, having scientists, and especially future generations of scientists, that do not use machine learning as a black box, but actually understand the intricacies of how it works and how to properly apply it to data, and how to properly ask questions and understanding the answers that you're getting out of it. This will make a big difference also for for the future decades of science. So, fields are very much interconnected, and what you learn in one can be applied in another. And really, I want to, if there's something I can, emphasize, is understanding why you're doing what you're doing, and not using, tools as black boxes, or oh, someone figured it out, so I'll just use it as is. This is what's going to make you a better scientist than, someone else. And so really earlier on, as early on as you can, try and keep that in mind and pay attention, because it's a pain in the butt to go back and have to relearn it because you thought you didn't need it, and then you do. So really, do yourself a favor and try, and it's really hard, but to keep the big picture in mind, is one piece of advice I would want to give you, because this is something that now we're going to need in astronomy, is how to piece together all of those different experiments and know very well how to make it work, because the things you don't know are the things that are going to bias our measurements and our understanding of things.
Yeah, I totally agree. And I wish I would have gotten that message when I was younger too. So yeah, I'm glad that you're giving it to them. Maybe, I mean, we could, the more you speak, the more questions there are. I think it's just a sign of people's interest in this, which is fantastic. But maybe we can pick a couple more, and then we can leave you be with the rest of your day. So I think there's a couple of questions that I think are correlated. I'm going to mash up two questions. So one is, has dark matter been observed? And if not, how do we know that it's responsible for all the phenomena that that is associated with? And then maybe another one, which I get these kind of questions all the time, and I'd be interested to hear your take on it, which is dark energy and do dark energy and dark matter really matter? Or is it just something exotic? Is it something that we're just doing because we got nothing better to think about? Or does it really matter on the grand on the big context? So
yeah.
So this is, has dark matter been observed? And then, how do these things really matter?
So here, that's why I like to go back to the words that we use, because all of these questions, you can come from the understanding that this is dark matter. It's that thing where we've decided it's a thing. It's like that. And then we just can't see it, but we already know that it's that thing that we can see. Not quite. Dark matter is a concept. What we know is what we can see. We can see that there's, something with humongous gravitational potential. And so the only thing that we know is it's very heavy. It doesn't emit light, and and it clusters. And so this concept of something that doesn't emit light, so doesn't interact through electromagnetism, and that is very heavy and interacts through gravity. That concept, that whatever satisfies those two conditions, since we do not know more, we need to give it a term, because that concept of that thing, that blah, 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 that's a very long sentence. So what's the name that you're going to give it? You're calling it dark matter, because it's a type of matter, right? It has the weight, but it's dark because us as humanity don't understand. We know nothing about it, right? It reflects our understanding of it. So in that sense, we only have indirect proof of dark matter because we can't see it. But yes, we've observed it. We've observed how dark matter interacts gravitationally, so through gravity, with other things. So yes, it's been observed. And then to the question, well, is it exotic? Are we doing this because we don't know what else to do? Again, it's if you decide that we're not talking about things, we're talking about concepts. We're talking about phenomena that we've observed. The universe is accelerating faster and faster. There's something that is pulling things apart. If it exerts this action on things that we can see, it's a force, and force and energy, are interconnected. Okay, so there's this energy that are doing things that we're seeing, but we don't know what it is. And our lack of knowledge, again, is giving it the term dark. So we are seeing, we're measuring, we're actively having this information that something is very heavy and pulling, and pulling things together, and something actually on larger scales pull those things apart. And we've given them names, and we only know, a couple characteristics for each of those. And then we're trying to figure out what would match these characteristics. And that's really, and it's important to focus on that, because that's also 95% of what's happening in the universe. And, we feel as a scientific community, especially cosmologists, because that's what we do, we feel that figuring out what's happening with 95% of the universe is probably a good use of our time.
Yep, absolutely. So I have a couple of administrative questions that I've been receiving that are not directed to you. I'll answer them in a second, but maybe I was seeing one last one or do you have any ones that you want to answer? Because I was looking at one that maybe would be a good one.
Go ahead, because I haven't looked at questions in a couple minutes.
Okay. Yeah, there's a lot of them. So you touched on the role of programming in data analysis. So this one I think is asking more broadly, what is the role of simulation and numerical modeling, understanding complex cosmological phenomena? So you touched a little bit on it, but maybe can you elaborate on that?
Yeah, it's very important because when I talk with my friends that are biologists, we always they were telling me actually about scientific honesty and how this colleague that they had just redid an experiment and hit a mouse because blah blah blah. And that's the point, right? In other sciences, you can do and redo your experiment, and that's how people get confirmation and get a consensus. Different teams are going to redo the experiments, and then they all find the same more or less, and then that's it's a consensus. But for us in the astronomy community, yes, different teams are doing different analysis or maybe the same, but the data, there's only one set of data. We cannot rerun the universe, and so that means that we need to be super ingenious about other ways to keep ourselves, to extract as much as possible from the data, but to also keep ourselves, intellectually honest. And one way to phrase it is humanity as a whole, all the teams, everyone, we all have the same set of data, right? We will never produce different sets of data. Even it takes us, collaborations of thousands of people to make this map that I was showing you. And then as soon as we have it, it's public for the world to see. And it costs 65 million to build. So no one else is going to build another one of the same. So we kind of that's why you have different experiments and different that are looking at different things. And then as soon as you collect your data, it becomes public and it's everyone's property. So the differences between the teams are not the data, but really how they analyze it and how they're looking and considering their data. And what I'm getting at is, if you want to make sure that you understand what you've observed, the easiest, actually not the easiest, but the only way that we have is to say, okay, I understand that the universe works with the laws of physics. And then I think that also, this happens and that happens, and this is my theory. And what you're doing with all of this is you're creating a fake universe. And these are the simulations. And different teams create different simulations. And, it's very time consuming, as in computing time. So they try to find better ways to make them faster, or the simulation, because it's so detailed, is a very small part of the universe. But actually, to do certain types of analysis, you need bigger, to simulate bigger chunk of the universe. So simulations are a very, very, very important part of our analysis, because that's where we put, it's basically what we're trying to do is, we've tasted a cake, but no one else is going to make that cake again. So the only thing we can do is look at, the list of ingredients that we think exist overall, and then make a selection of the ingredients that probably went into that cake. So that's one. But then two, also, in which order do you add them? In which quantity? How do you bake them? All of that. And that's the simulations. Everyone's trying to recreate the recipe. And then, you look at the cake that you've made, and you taste a piece, and you taste again, and you go to the original one, which is your data. You're it's still not the same, but this friend's cake is closer than the one I did. So probably they have better chosen their ingredients, or they have better chosen their method to bake them. And that process is really the simulations. So creating fake universes for us to compare it to the real data that we're taking, it's actually like an overwhelming part of this, the process and all the activities that are happening in astronomy is trying to create the best, most reliable and close to reality simulations as possible. And this is a very big area of development, and this is a very big area of work, again, for the next decades.
That's great. I really love that cake analogy. I'm gonna have to steal it at some point. So in fact, I was going to address some administrative questions, but I don't know actually if this is like administrative or just more like pep talk. So I'll read it to you, and I'm happy to answer it as well. But I think maybe it's addressed for either you or me. Oh, and I just lost it. I have where is it? Here, give me a second. Let me see. I had saved it. Nope. Lordy, I lost it. It was about, I think I can reconstruct it if needed. But the question was, oh no, here, I found it. Just being a little philosophical. What if one gets, say, hundreds of rejections? Does that mean that I am not for physics because 100 people have thought that I can't collaborate and do the research? It's just too discouraging. I don't know who else to ask. So I guess the question is, how do you deal with rejection in the academic setting? I read this originally as they meant for the mentoring program that they've been rejected, but I don't know if that's what they meant. But I think maybe just more broadly, how have you dealt with rejection in the past? And, when do we say, okay, maybe we're not meant for that field? And when do we say, we just got to keep trying?
That's a really non-straightforward question to answer. Personally, whenever I was told no somewhere, I would just go somewhere else and ask again. So that's how I deal with rejection. Now, I think something that helps though is not focusing on what other people are doing or saying, but first having a very clear picture of what you want to try and accomplish. And do you want to, because I don't know which level, if it's high school or getting into a bachelor program or a PhD program. So the answer is going to change as well, depending on the level. But overall, having an understanding of what it is that you're trying to achieve, either by pursuing a degree or, getting an internship. Are you focusing on what skills you want to learn? Like, what is what you're trying to get out of the action or like the application that you're submitting? And then if you focus more on the things that you're trying to get, so the skill set, the knowledge base, if you reframe it that way, you might find other opportunities to get a certain skill set, to get a certain understanding that you're trying to go for. Because I know that, being French, we have a very elitist and simplistic way to think about how we go through our studies. And if you're not selected to one of those 3 schools, then you're never going to make it to a PhD program. And if you don't do then you're like never going to blah, blah, blah. And I find that utterly and incredibly stupid. And if your goal is something very well defined by society as, a program or something that's named, sometimes going after those goals is not the proper way to frame it. But if you're more focused on really what you're trying to get by entering this program, by working with this person, by applying there, it's not the name recognition, but it's actually a certain skill set, a certain experience, a certain whatever. If you're more focused on these, you'll find there are many other places that can, and you probably need to break it down. Maybe you're gonna, apply for another program, or just like go even in a slightly different field, and you'll get these skills. And then that will allow you to then go to maybe another place and get that experience, and just mix and match. And along the way, you'll also find maybe other things you're interested in, things that overlap and connect, and just like another field that allows you to go at what you wanted to do, but from a different angle. And so I think really focusing on what you're trying to get out of the things you get rejected for will allow you to maybe reframe and think about different ways that you can go about getting those skills and those experiences, and focus less on the shape that they take, and more on actually the substance that you're getting out of those things and those experiences that you're going for. That would be my way of thinking about it.
Yeah, I mean, that sounds really great. I think maybe just to echo that, I mean, I've gotten plenty of rejections in the past, including places that I've ended up working and I've been rejected in the past. So it's common. It's, you have rejection, I think, is part of the process. And for me, I think maybe echoing some of what Satya already said, I mean, for me, what was useful was to understand the way that the decision making was made in the different institutions. What is it that they were looking for? So, for example, going into grad school in the US, I studied, what were the metrics that were used in the selection processes for my for my areas of interest. And then I tried to be as honest as possible with myself. So I didn't just apply to, for example, Ivy Leagues. In fact, I didn't apply to any Ivy League. And so I was trying to be honest with myself as much as possible. So learning about the process, learning about where you want to be, and also learning about yourself and being honest with yourself will help you, figure out, if those rejections are reflecting something about, what is it? Is it about the lack of skills, as Satya was saying, which you can then build upon, right? Or is it something about the field, or some combination of those two, right? And depending on the answer to that, then just waiting for another round, working extra hard on whatever it is that you need to do to meet those criterias. Or just maybe going elsewhere, building skill sets, and in the process, perhaps you decide that you want to go somewhere else where you're not rejected and welcome instead. So hopefully that helps. I'll take the liberty of answering one administrative question, which I think kind of echoes what others are asking out there. So this is a question that is directed to the REYES team regarding updates. The person says, I've applied for both the online classes and mentoring program. I had been receiving emails after applying for the I haven't been receiving emails about applying to the mentoring program. I've sent an email to the REYES team regarding issues, but I haven't received any responses yet. I'm concerned that I won't be receiving any emails about it, and I would appreciate your help regarding this. Yeah, sorry about this. So let me just say, frankly, the person that is managing the email account is me. And so I'm juggling 1,000,001 things right now. So I apologize for not responding rapidly enough. So those of you that apply to the mentoring program, I pass on that information now to the mentors who should be getting back to the students that they will choose to mentor. If you don't receive a match with a mentor by Wednesday, that means that you won't have found a mentoring group where you can work one-on-one. That said, I'm creating a mentoring platform where we're going to be able to, those of you that are interested in nuclear physics will be able to join regardless of whether you signed up for the mentoring program or not. And so you will be hearing about this, and I will get back to you about all that. Regarding the classes, what we have, the only class that we'll have live this year is the Python for STEM. And that starts tomorrow, and all of you are welcome to join. I think as Dr. Gontcho A Gontcho said, programming is key for every field out there, including cosmology, but in every field out there. So Python is a great entryway for you to learn about programming. So I would strongly encourage you to jump in on the bandwagon. And we try to make it as fun and as accessible, assuming no background in programming. So just come join us tomorrow at the same time at noon Eastern time. Same link. All the lectures will be in the same link. So just come. And I think I've addressed all the issues in this question. Again, I apologize for the delays, and I appreciate your patience as we're, just trying to work on this as effectively as possible. I think, Satya, we've taken plenty of your time. We're so grateful that you've taken your, I guess, afternoon/evening to join us and give this really wonderful lecture. One question I did see that I forgot to mention. Some people ask if you're going to share your slides. It's up to you. We can make them available. We can figure out a way, or is there a way that, is there a link out there where your slides have been previously available?
We can figure that out. I can make them available for this.
Okay, sounds good. So thank you so much. Very much appreciate you. And I hope to meet you sometime when we're both in the Bay Area again. And until then, have a great summer.
Nice.
All right,
Great
take
job.
care.
All right, bye.
Tom, how are we doing?
Doing good.
Okay, awesome.
Hold on.